Alright, welcome to the first video in a series of videos that will be designing a model rocket capable of thrust vector control. In these dark times, we need something to do to pass the time. So, what is thrust vector control and what are model rockets? Well, everyone knows what real rocketry is. They're shot up by SpaceX and NASA and other companies. And what thrust vector control is essentially controlling the direction of the exhaust gases in a way to steer the rocket or maintain some sort of stability. For instance, if the rocket starts tipping to the right, then you're going to want to angle the thrust to the left to counter that torque, and vice versa for the other directions. So what I want to do is apply this to a model rocket, which has been done. You can find some videos on YouTube. But I felt like it'd be a nice engineering challenge for myself and a few others that I'm working with. So this video series will essentially walk through the entire design stages from the beginning all the way up to when we start developing and actually building this rocket. And hopefully, eventually by the end of the summer, we'll have something that's actually flyable. So for me, whenever I start designing a model rocket, I want to use some software that is somewhat simple, and this is an open source rocket simulation building and simulation software that you can download for free. It just runs on Java. It's called OpenRocket, and you can download it from their website. It does require Java to run, so make sure you have that installed as well. So with any rocket, if I go back to our little picture here, the outside structure is pretty much comprised of a nose cone, an airframe, and then in model rockets you have some sort of fins, but in these rockets you don't need fins because you have thrust vector control in order to keep the rocket stable. For this design, we're going to include fins for at least the development of the control stages, but the fins are going to be removable. So once we have a working controller that can maintain stability, and we can remove the fins and we know that it's going to fly straight. So for now, we're going to start with a rocket that has fins. Now, I've been designing model rockets for about 4 years now, and my experience at least from what I've worked with, is I like to have a minimum airframe diameter of 4 inches, mainly because it's easier to work with. You can fit your hand in if you're a normal sized person, unless you have gigantic hands. So we're gonna make the base diameter, which is the nose cone diameter, 4 inches. And then the whole purpose of designing in this software, by the way, is mainly to get an overall layout of the rocket. It doesn't have to be perfect because we're going to develop this rocket in a CAD software as well as the controls and simulation in another external software as well. So this is just merely a starting point that we want to use. There are plenty of options for nose cone shapes. You can have conical, which is like a triangle. The ogive is a nice little point at this, pretty aerodynamic. But I'm going to choose the ellipsoid just because it's a little bit safer if it comes down, and it's less chances of actually damaging the point. So that's going to be the beginning of the nose, at least the nose cone shape. And the next thing you want to do is have a shoulder, because it's got to be coupled to an airframe, which is simply going to be a cardboard tube. So we're going to make the length at least 1 diameter's width and length, and then this is going to be 3.9 inches. The reason I'm choosing 3.9 inches is, you'll see if I go to this nice little website called Apogee Components. Is a nice source. You can pretty much find anything you need to develop model rockets, including kits and parts. The reason I know it's 3.9 is the diameter that I want for that shoulder is if I go to the 4-inch tubes, I think it's on page 2, maybe. Oh, these are all 3 inches, 3 inches. Let's just go to the 3rd page. The 3.9 inch lock body tube. So the outer diameter is 4 inches and the inner diameter is 3.9 inches. So that's why I'm choosing 3.9, because it's going to slide right inside that tube for a nice slip fit. So the next thing after designing the nose cone is you want to include a body tube. Now they come in, the inner diameter should already match the shoulder, but this is open source software, so it doesn't always work that way. The outer diameter is 4, the wall thickness is 5. All right, cool. And if I go back to the Apogee site, you're gonna see that they come in 37-inch lengths. So we're just gonna use that. For this rocket, I just want one single airframe. In more advanced kits you can find that have dual deployment for parachutes, they'll usually have a split section, so it'll be comprised of 2 tubes with a coupler. But for this, because we're gonna be developing a low power rocket, we're not gonna be hitting altitudes where you need dual deployment parachutes. So we only need one parachute, which can separate them between the nose and the airframe for recovery. So we're just gonna say 37 inches, and that's our tube. Now, we are gonna be using removable fins, and what I did when I did the NASA student launch competition is we included a removable fin can system, which essentially had slots in the airframe for the fins to slide into, and then we had a boat tail. This is what we came up with the name, obviously. We had a boat tail that served as the cap, or it holds the fins in place. So we're gonna do a little transition thing here. I like the rounded, it's a nice aerodynamic property. It creates less pressure drag. And then the length, I'm just gonna make this 1 inch because it doesn't have to be that long. And the after diameter is gonna be 3 inches, and you'll see why in just a sec. Close. So the reason I made this aft diameter 3 inches is that we're gonna have a motor tube, or an internal tube, that's gonna house the motor, the thrust vector gimbaling system, which I'll show you. So there's multiple ways you can actually control the thrust. What we are gonna do is we're actually gonna control the angle. We're gonna gimbal the angle of the rocket motor itself. So it's gonna need room to play in there. So we're gonna do a 3-inch tube that can house all of these components. So let me go to edit. The outer diameter is gonna be 3 inches, and the inner diameter is gonna be 2.9. They tend to have the same wall thickness. And then the length, I'm gonna give ourselves 10 inches. This is kind of arbitrary, it can be changed for now, but let's just say 10. And then I want this to be offset because the boat tail, we're pretty much gonna 3D print a lot of parts. And to avoid any exhaust from actually hitting this boat tail, we're gonna go the other direction so that this tube can sort of insulate the plastic 3D printed parts from any exhaust gases that may touch the outer edge. So that provides our inner tube. Now, in order to lock the inner tube to the outer tube, we're gonna use centering rings. We're gonna use 2 of them to be exact. The outer diameter is already 3.9, the inner diameter is 3. It already snaps to our 2 tubes, which is nice. These are gonna be probably made out of some sort of thin plywood. So I tend to do 1/8 of an inch thickness for these. And then we're gonna put one right at the very top. I wonder if this has to be 8.875. Yes, that way the top edge is flush with the top of the tube. So that's one of them. And then we're gonna include one more. And let's make it 2 inches down. So if that one was 8.75, so this one's gonna be 7.875 in the negative direction. That's 1 inch, so let's do 6. And actually, I want this to be up a little bit, so I'm just gonna do an even -7. For those of you guys wondering why I'm using an on-screen keyboard and there's this little bar down here, is I don't have access to control my arms, so I merely control my computer through the motion of my head, where the mouse is moved through the tracking of my head, and then this little bar down here allows me to click, where all I have to do is stop moving for it to click. Boom. Let's make this the 0.125 again. those are our centering rings, and we're done. So now we have our centering rings, we have our boat tail, so the last thing we need to include down here is going to be actually our fins. So I'm going to use a trapezoidal fin, just out of preference of my little experience. They're nice triangular fins where like the back end is a triangle, are more easily damaged. And you could do other types of fins, elliptical, freeform, and whatnot. But traditionally, I'll just stick with the trapezoidal fins. We're going to use 4 fins just for pure symmetry in 2 planes. The root chord is essentially the length of the bottom of the fin. So we're going to do a 7-inch root chord, which will allow the fins to butt up right against this centering ring and then be capped with this boat tail. And then I'm going to make the tip chord, which is the top length, exactly half of that, 3.5 inches. And now to make this symmetric about the center axis, the sweep length is essentially the length from this tip to the beginning of the tip chord. So we want this to be exactly half of, well, a quarter of the overall length. So it's going to be 1.75. And then the last thing we need to do is the height of the fins. I'm going to do 4 inches just for now. We may have to change this in a little bit when I go over stability. But for now, let's just make it 4 inches. So we have our fins. Actually, there's one more thing I needed to do with these fins that I totally forgot. Because they're going to be through the wall fins, we need to include tabs. So the tab length is essentially what's going to go through the wall. So we're going to keep this at 7 inches as well. And then the height is going to be 0.5. So that would go from this outer frame into this, so it actually slides along this. All right, so that's actually our fins. And we'll get into more details later when we actually get into a CAD software. The whole purpose of this is essentially to lay out the rocket so that we don't forget any components, and then once we have a layout, we can then go to our respective CAD softwares and then fully design the rocket we want. All right, so now we have our fins, we have our airframe, the motor tube. So inside the motor tube, we want to include a motor. So we're gonna go back to edit and motor, and we're gonna say this component is a motor mount, which means a motor will be inside of it. So now that if we wanted to, we can move into motors configurations, new configuration, and we can select motors. Now this software has a database of pretty much all types of model rocket motors, all different brands. With the current pandemic or epidemic or whatever it's called right now, all high power launch fields are closed indefinitely. So we want to work with low power motors for 2 reasons. One, we can launch them in our backyard if we want, or a park if it's local enough and there's not enough people around, so we can maintain social distancing. And the other fact is that low power is, 1, is cost effective, and 2, is less dangerous, because we are going to be controlling this rocket and it could possibly be steered out of control. We don't want this thing going anywhere close to a Mach number. So we're going to stick with your SD's rocket motors, which you can purchase at local stores like at Hobby Lobby or Michael's, which is interesting. But we're going to use this F15 motor. The reason I want to use the F15 motor is it's got a decent burn time of 3.5 seconds, which gives us 3.5 seconds of control. But the other thing is that it's got a level thrust curve, which I'll show you in a later video, which means the thrust is close to constant from the beginning of burn to the end of burn, which is a nice feature to have. So that is how we added our motor. The next video, I'll go into simulations and you'll actually see how this motor can be, how it actually will affect the rocket's flight. All right, so now that we have the external structure of the rocket built, we have our motor selected, there's 3 more components we want to include in this, and one of them is going to be a ballast system to the nose cone so that we can control our center of gravity. The second thing that we need to include is a recovery system, which includes a parachute and a shock cord. The shock cord tethers the parachute to the rocket. And then the last thing is going to be we're going to add a mass block for our electronics system, which is going to be the brains, the flight computer for the software. It's going to be the brains for everything. So let's go ahead and add the mass for the nose cone, which is going to be our ballast system first. So you click on nose cone and then you hit mass component. This allows you to choose any mass. I'm just going to say 1/2 pound for now. You'll see why in a minute. And then the size is not really important, and we're not going to be outside the rocket. We'll just go kind of inside the nose a little bit. All right. So now that we have a mass thing, and if you didn't notice, this center of gravity symbol here was really close to this red dot. And by adding that mass, we moved center of gravity up the rocket. Now, I'm going to talk a little bit about stability now because I just mentioned the center of gravity, and the ballast system is mainly for stability. Now, in model rocketry, stability is a stable rocket is essentially where you have your center of pressure, this red dot, being located after the center of gravity if you're going from the beginning of the nose cone. The reason you want this is the center of gravity is where all gravitational forces act on the rocket. So as it's flying, all gravity is going to be acting at this point. The center of pressure is similar to that, except this is the point at which all aerodynamic forces, so any drag or any side forces that could be caused due to wind, act here. Now, if this red dot was before the center of gravity symbol, any horizontal wind or disturbance can actually make the rocket essentially rotate and then essentially drive back into the ground. With it being after, what it does is essentially steers into the wind and maintains vertical flight. And typically what they like to see, at least with NASA, when I did the NASA competition, is you want the distance between these 2 points to be at least 2 times the diameter of the rocket. Now, we're going to be controlling the rocket through thrust vector control, so I'm okay if the stability gets low. And if you right now, it says 2.05 cal, so it's 2.05 times longer than the diameter of the rocket. But you can modify the stability in 2 ways. You can add mass to move the center of gravity, or you can change the aerodynamics by changing the fin sizes, which changes location of center of pressure. But I'll get to more details about stability and flight characteristics when we get into simulation. But for now, let's move on to the design. So the next thing we want to include is a parachute. So we include this nice little parachute. You can resize it and do all these kinds of things. You can actually do all the drag characteristics of the chute for recovery simulation. I'm not too concerned with that. All I care about is the rocket coming down safe. So I'm just going to put this as a placeholder for a parachute. The next thing you want to include is a shock cord, not a streamer. I included a streamer. A streamer is another way you can use instead of a parachute for really small rockets that you can buy like at the store that are like your SDs, like C motors or B motors. They're very, very, very low power. You can use streamers because the rockets are so light, they don't need a parachute to actually come down. All right, so we want to add shock cord. And what this does is tethers your parachute to the airframe. And for when the parachute actually fills up with air and provides a shock, that this also does is it has some sort of elasticity characteristic to allow it to expand or stretch as a shock, so it dissipates throughout the cord, which is nice because it creates less impact or disturbance to the frame of the rocket. So we now have our parachute, our shock cord, and the last thing we want to do, I'm going to make is a mass component, but this is going to be our electronics bay. Let's do it from the bottom of the component, so it's going to be closer to there. Of course, it's going to be like this. So we're going to do -10. It's going to be kind of right above our motor because that's where we're going to be controlling this motor. So that's, and I did mention that this is like the third of the last things we didn't include, but I'm going to include 1 or 2 more things as placeholders. They're going to be bulkheads, which are there to protect any electronics. So one bulkhead will prevent any exhaust gases from getting to electronics, and then we'll add another bulkhead. Just double click, I don't even know what happened. We'll add another bulkhead to be -12, or 0, to prevent any ejection charge as powders or gases from hitting electronics as well. Because when you eject your parachute, you typically do that using black powder explosive charges, which can be pretty volatile to any electronics or sensitive electronics that you're gonna have. So you want to protect it. So this is what those two bulkheads will do. And like I said, this is merely just placeholders. We're not actually gonna design the full rocket here. This is just a nice way to get the layout and just kind of bookkeep all the components that are gonna go in your rocket. So right now, I'm gonna end this video here. This is just a generic design of the layout of the rocket. The next video, what I'll do is we'll tweak some of these components and we'll look into the simulation aspect of OpenRocket itself before moving into a more sophisticated simulation environment. But that's it. Thank you. If you like this video, make sure to drop a like or a comment below, and please subscribe. Thanks.